All right, let's go through this process one more time. So we're going to have a function, in this case, f of x equals x squared. We're going to have an interval, in this case 0 through 8, and we're going to be doing a right-hand Riemann sum. But in this particular problem, we're not going to have a specified number of rectangles. So it's going to be a formula that we could come back to and use later on. So the steps are as followed. First step, find delta x, which represents the width of each rectangle, even if we don't know how many there are. Then we're going to find x sub I, that is each of the endpoints as a formula. We're going to plug that in to our function. We're going to set up our sigma. We're going to simplify that and break it down, and then substitute using these three formulas. Notice I only need I squared because I have an x squared. So, first things first. Here is the formula for finding delta x. So b, which is 8, and 0, which is a, would give me 8 minus 0 over n, or 8 over n. That is my width. So if I were to tell you that there were 8 rectangles, we would plug the 8 in for the n, and we would know that each rectangle had a width of 1. If I said, let's use 4 for n, 4 rectangles, each would have a width of 2. If I said, let's use 32 rectangles, you'd plug in 32 and you'd get out 1/4. Now, we can also use delta x, which is 8 over n, in our next piece. That's why it's not step 1. So we're going to get a, which is 0, plus 8 over n times I. So I'm just plugging in the a and the delta x that I just found. I'm going to simplify that, and that's going to be 8I over n. Step 3, plug in x sub I into my function. My function is x squared. So take what I just found and square it. The result, 64 I squared over n squared. This expression represents the height at any endpoint over my interval. Set up the sigma. Sigma from I is 1 to n of the height, which is 64, I squared over n squared, times the width, which was the delta x, which is 8I over n, nope, that is not correct. Keep doing that. It's actually just 8 over n. That's from step 1. And if I simplify the inside, it's going to save me a little bit of work down the line. I get 8 times 64 is 512 I squared over n cubed. So when I say set up the sigma, I'm looking for something along these lines. And now let's break it down. So there's only one term, and by that I mean there's only one monomial here. There's no addition or subtraction. It's all multiplication and division. I want to set this up so that I could use one of these formulas or more later on. So to me, that means I need to take out the 512 and the n cubed, meaning I'm going to basically put it in front of the sigma. So 512 over n cubed times the sigma of I from 1 to n of I squared. Okay, so again, let's just break down that whole process. We have our width of each rectangle. We use that to find our endpoints. We use the endpoint formula into our function to find the height at each endpoint. We multiply the height at each endpoint by the width of each endpoint to get this expression, which represents the area of each rectangle. And since I'm using sigma, that means I'm adding all of the rectangles from rectangle 1 to rectangle n. And in order to proceed, we're going to factor out anything that's not an I so that we can now substitute. So we're going to get 512 over n cubed times the n squared formula, or sorry, the I squared formula is right here, so it's n plus 1, and then 2n plus 1 all over 6. And that's our formula. We could simplify that. We can do all kinds of different algebra to that, but we're going to talk about really applying some calculus to this. Okay, so this is a formula for the area under f of x equals x squared from 0 to 8 using n rectangles. So if I wanted to plug in 8, I can plug in 8. If I wanted to plug in 1,000,000, I could plug in 1,000,000. But let's talk calculus, and let's specifically talk limits. Okay, let's look at the limit as n approaches infinity of that above expression. I'm actually going to reduce. I'm going to say 256 and 3, so the 6 reduces the 512, n plus 1, 2n plus 1. And what's great about limits as n approaches infinity, we're talking about end behavior. And if our end behavior is a rational function, which is what we have here, the only thing that matters are the dominant terms from the top and the bottom. So the dominant term in the top would be 256 times n times n times 2n. So we would get 512 n cubed on the top, plus a bunch of other stuff that's not going to matter. And the bottom is 3n cubed by itself. Now, all of this other stuff doesn't matter, and we can focus solely on what's left. Notice that the n cubes are going to cancel, and we simplify down, and the actual area under the curve is the fraction that is remaining. 512 over 3 is the answer. So instead of plugging in an actual number there, we're going to find